In terms of scintillators, why would this be a device that anyone would be interested in? Really, it's the water equivalence that makes the huge differentiation between this and other detectors. So really, you're not perturbing the beam right there at the point of measurement for those MV photons and electrons, which eliminates all of those other correction factors that go with that perturbation in order to get back to dose to water. We can make them very small, which helps with that small field dosimetry in terms of volume averaging. They don't show dose or dose rate dependencies for standard MV beams, photons or electrons, and again, energy independence for those as well. The beam quality correction factor for our scintillators is unity, which really does reflect back to that water equivalence. There is a slight temperature dependence. It's about 0.1% per degree. So if you're doing everything at room temperature, you can usually ignore the temperature corrections. And then there's nothing ferrous at all in the detector itself, so it can be used with MR Linux quite successfully. We do make a longer fiber for that situation so that you can keep the electronics outside the 5 Gauss line. So make sure to mention that if you're asking for a quote for the scintillator, but it does work quite well with the MR Linux as well. Our scintillators are organic. It's an organic plastic that is 1 millimeter diameter, 3 millimeters long for the first generation device, the W1, and then with the W2 we have both the 1x1 and the 1x3 millimeter active region. So you have a slightly longer fiber, gives you a little more signal. You can compare with all the publications that have come out for the W1 because that fiber is absolutely identical. We actually don't earmark them as W1 or W2 until they're ordered. They're made the same way in terms of the actual optical fiber. The one difficult part, and usually the biggest learning curve for people when they're getting into scintillation dosimetry, is accounting for the Cherenkov light. So this, as I'm sure most of you are aware, this is light that's generated by electrons traveling faster than the speed of light in the medium, creating this kind of broad spectrum, usually looks blue sort of glow, like the picture I have here, a standard picture of the reactor coolant pools. The method we use for correcting for Cherenkov is a 2-channel chromatic correction based on a publication from Matthew Guyot in 2011. And I'll explain a little bit more about that on the next page. But that really was what enabled us to put this into a commercial device and make it easily used by a wide variety of users across the world. You do have to give it a known dose in order to tie the signal to dose. It is not what the national standards labs would call an absolute dosimeter. It's something that does need a comparison with a known dose. And part of that is really because as the plastics receive higher and higher doses of radiation, they discolor. And because we're relying on the optical light from the scintillator, that discoloration causes a decrease in the signal. It attenuates the signal, as well as shifting the spectrum just slightly because it's a preferential attenuation in a certain portion of the spectrum, which requires a recharacterization in order to make sure that your Cherenkov correction is accurate. I should say that decrease in signal is usually about 2% per 1,000 gray that the scintillator receives. So it's not a super rapid decrease, but it is one that you would want to keep track of and periodically recharacterize and recalibrate. This 2-channel chromatic correction that we use is kind of illustrated on the figure on the right here. We have a blue scintillator, and Cherenkov is a broad spectrum light. So we split the signal into 2 portions of the spectrum. We call them blue and green. And we have you do a set of characterization measurements where the dose to the scintillator is kept the same. And we change the amount of optical fiber in the beam, so the Cherenkov signal is the only thing that changes with these measurements. So with a change in signal in each of the channels, we can create a correction factor based on these 2 measurements in what we call the minimum fiber configuration and the maximum fiber configuration. The ratio of the change in the blue signal versus the change in the green signal gives us this Cherenkov light ratio correction factor. Subsequent measurements then are corrected using the signal in the green channel multiplied by that CLR correction factor to remove the Cherenkov signal from the blue channel and leave you with just scintillation signal there. With the W1, we had created a solid slab that you can have your minimum fiber configuration with the fiber coming straight out of the beam, or that maximum fiber configuration with the fiber wrapped all the way around. This is still available as an option with the W2, so if you're planning to do solid phantom measurements, it's a nice one to add on, but it's not included automatically in that package, just so you're aware as you're looking at those quotes. We do include a smaller bracket that's used for water tank CLR measurements. It was also designed so that it could be used in fields or in machines like, for instance, the CyberKnife that can't do a large 30 by 30 field in order to irradiate this entire maximum fiber configuration setting. So it has the smaller jig there, but really the principle is the same. You're doing those two characterization measurements in order to characterize that stem effect to be able to remove it for subsequent measurements. If you want your output in terms of dose, it's really just a scaling factor then to convert this signal into dose. So you would, after you do your CLR characterization, you give it a known dose in a reference field size, and that conversion factor can be determined. So that first device that we made was the W1. It has been on the market since 2014, and as I mentioned, it has that 1 millimeter by 3 millimeter active area at the tip of the scintillation, or at the tip of the fiber. There are quite a few publications available for the W1, but one of my favorites is that TRS 483, which is a wonderful document for small field dosimetry. We understand that that's fairly complex, but it really does help with detector-specific information about small fields. But one of my favorite parts of that is that in the tables where the scintillation, where the W1 shows up, correction factors are unity for every single field size that they list. Then they list based on energy, with and without flattening filter, these output correction factors for small fields. Just to be aware, if you're not familiar with the document, places where they don't list information for detectors, that really indicates that either the detector wasn't appropriate, or the variability of the measurements was too high for them to recommend the use of that detector in those small fields. The limitations of the W1 as that first generation device is that it was really designed to be a single point measurement system. We were trying to solve the output factor problem at that point. So it wasn't designed specifically for use with water tank scanning systems, although it is waterproof. It can go in the water just fine, but it won't interface with your water tank scanning electrometer. It does currently require a 2-channel electrometer in order to do the Cherenkov subtraction calculation, such as our Supermax electrometer. So the next generation, of course, the first thing everybody wanted to do was scan with it, and also we had a lot of requests for a uniform size of the scintillator so that volume averaging concern would be decreased. So we improved the optics, and we combined that with the electronic signal processing circuitry and created a new electrometer called the Max SD. So the W2 fibers are user replaceable fibers that are used with this dedicated system. We provide it with the 1x1 and a 1x3, so you have both that high resolution and the higher signal matching W1 geometry fiber that you can use as appropriate with your systems. The other advantage of this, as we were designing, of course, was with water tank scanning in mind, is that for every 10 millisecond integration, the Max SD will do a Cherenkov correction of the signal and convert that corrected signal into an analog output, a current output that's sent to your water tank electrometer via simple triax cable. So the way that looks in setup is you have your W2 fiber. We have an adapter sleeve so that it can match the standard chamber holder of anybody's water tank. That's so that you can get this tip out away from some of the scanning apparatus. It can fit without you feeling like you're going to crush the fiber or anything like that. This really is just to enable you to use it with the water tank. You hook up the optical fiber then to the Max SD as the input channel for the Max SD. Make sure that you have selected your saved CLR file that you want to use for this particular fiber. If you, would assume you have an individual one for your 1x3 or your 1x1 fiber. Some people like to have it for individual energies or machines, but that's not necessarily a requirement. And then that triax cable is attached to the output of the Max SD and the input of your water tank scanning system. And from the point of view of the water tank, it looks just like a diode. It's a detector that you don't put a bias on, but when the beam's turned on, the water tank electrometer receives a current. This is just a close-up of that minimum fiber and maximum fiber configuration if you haven't done your CLR measurements yet. Otherwise, you can simply zero the Max SD, zero your water tank, and scan your electrometer. We recommend you scan slowly. You get the best signal to noise if you're doing individual measurements at about 1 second each or more if you're really wanting to get that signal to noise up or the noise down lower. But 1 second measurements are sufficient at each measurement point. So it's a slower scan, but we're looking at small fields again, and to take the time to do it right really is beneficial in the long run. It's worth that little bit of extra time not to have to worry about all the other corrections or conversions that might go into a small field scan. The proof is in the pudding, of course. So here's one of the initial publications about the W2 when it was first released. From NYU Langone. This was Indra Das's group, although he has since moved to Chicago, I believe. But they compared W2 scanning with film measurements. This is a 1x1 field and got excellent results. They also verified what we already knew with the W1, which was that there isn't a dose rate dependency. They tested it up to 2400 MU per minute with, I believe that must have been the FFF beam, and they didn't see a dose dependency either, up to 4000 centigrade. Another interesting publication that I like to bring up comes out of Richard Popple's group from the University of Alabama at Birmingham. And they were looking at variant hyperarc treatments with targets down to 3 millimeter diameter, comparing the W2 measurements with film. And they got very good agreement in those particular treatment planning comparisons. We do provide it with a localization marker because the one drawback of being a water equivalent detector is that when you try and image it for alignment and setup in a Phantom, you can't see where the tip is. So we have aligned localization markers, dummy fibers with a little BB in it for both the 1x1 and the 1x3 that are provided with the system. So that was all I had. I know you are all busy people, so I'm trying to keep it short and sweet. I apologize for talking quickly. I tend to do that. But if you have any questions, please enter them now in the question dialogue, or if you want to follow up with us later through the website at standardimaging.com. There's information through the customer portal in terms of user manual and such, but there's also brochures and things that are available through the website. Otherwise, thank you so much for your time. I do appreciate you all taking time out of your busy schedules to be here with me and to learn about this detector that I'm sure you've heard other people talking about.